My name is Mahmudul Hasan, and my advisor is Dr. Untrusted. Here, we are trying to focus on some interesting problems on the harder security field. So let me ask you a very basic question. Like, we are all familiar with the software viruses, right? That is attached to a program in our computer. That is attached to our any program in your computer, and we know how dangerous it can be, right? But do you ever think about virus that is far more harder? So normally what we do in case of software viruses, we apply some patches, and in our case, we install the web operating system, and we get the new computer like this, right? But what if in our regular day-to-day use hardware that is get affected by any kind of virus? We can't trade it, right? Because hardware is cost. I mean, it's expensive, right? So that's why there's a concern in the hardware security area, because in the day-to-day life, the rapid proliferation of the semiconductors are increased. And for example, in the case like her, there is about 2,000 to 3,000 microprocessor in a single autonomous vehicle. So that's we also saw the chip shortage in the last 2 or 3 years, because it's getting increased day by day. But the fact is, the top semiconductor vendors are 600 billion industry. They are fabless, and they don't have any control over the offshore industries like in Taiwan or South Korea. So as a result, the DoD has recently exercised on a zero trust approach. That means they don't want to trust any of the third party vendors, and they want to try to solve it from their own end. So how can they do that? That's a very interesting question. And one interesting fact is in 2014, the Department of Defense published a statistic showing that the 72% of DoD are not custom chips. That means in some way, some third-party vendors, they are taking it with those ICs. Okay, so if you want to talk about the IC supply chain, for example, if you have a problem and you want to solve it, right, and you need a custom IC to solve that problem, so you go to a third-party IP vendor and ask them about to solve your problem, and what they did, they write the high-level idea of your problem in a hardware description code, and they send it to the IC design house to design it in a specific technology. For example, 7 nanometer or 10 nanometer, right? And there can be any specific, for example, the clock cycle or the frequency, right? And based on that specification, the IC design house send it to the foundry, and we get the actual hardware. So during this IC supply chain, our design or our idea can be maliciously modified or overproduced by any of these third-party vendors. So there are some common supply chain security threats. Some of them are like the counterfeiting hardware or the reverse engineering of our IC, and there can be IP theft and overproducing. And the last but not least, the hardware Trojan. That means insertion of malicious circuit in our indicator circuit. So I mean, the problem we are tackling here, the hardware Trojan, is this actually real? Yes, they are real, because the US Naval Institute, they show in a news report that one of the supercomputers, Supermicro, was found to have a hardware Trojan on their motherboards. Also, researchers found that there are some secret cyber threats on the brain implants that can severely injure the patients. So we have a really serious problem, and there is no solution. I mean, no effective solution kind of hardware Trojan in the cost component. So, I mean, if you want to talk about the hardware Trojan, I mean, it's a malicious target, and it consists of two components: the trigger and the payload. The trigger consists of some input conditions. Based on the input condition, it can trigger, and the payload basically, it corrupt the output or somehow bypass some information from your IC. So in here, you can see the microprocessor, and this trigger is basically taking the inputs from the control signals, and the payload is nothing but it bypassing the registers data over the network, right? So in our work, we are dealing with the Trojans that corrupt the functionality of circuit. So, in a customer supply system development, we know that from design house to fabrication, they took part to design the whole IC, right? But when we buy the IC directly from the market, we are calling that the cost component. And the commercial off-the-shelf component provides several advantages because it's ready to use and you can deploy it in any of the system. And like if your system have aging and you can change your hardware and you can install a new cost component in your system. So it's easier to integration. And but the thing is, when we buy that cost component from the market, if any of these third-party vendors they insert the malicious Trojan, so how can we deal with it, right? So there are several approaches to detect the Trojan in an IC. For example, the side channel analysis or the logic testing, but none of them is applicable for the course because when we buy the cost component from the market, we are not sure which third-party vendor is tackling this IC lifecycle stages, right? So as a result, we don't have any golden design or net list so that we can analyze data for the cost component. So for this interesting problem, we are trying to propose a solution that we are calling software variant. And this solution is not about to change any hardware architecture or the modification of hardware. So what we do in our solution, so instead of running the original program in the cost processor, we are running two variants of it, and these two variants they are functionally equivalent, but the internal structure of these two variants is drastically changed. And finally, these output of variants are compared, and if there is any anomaly, we run the another variance that is significantly different the other two variants, and by doing the majority voting, we took a decision. So, but how can we generate this variance, right? Because there is no way we can use to generate those diverse variants. They are drastically different in their architecture. So let's first understand the internal activity of a microprocessor. So you can see here, we run two variant in a microprocessor, and in the same clock cycle, the internal activity of two variants are drastically different as they often goes from 0 to 1 on the same nets, right? So when an attacker designs a Trojan, they try to select this rare activation nets because if it's easily activated at the initial stage of the life cycle, so IC life cycle, so the IC the customer just threw out because they found the anomaly in the IC life cycle. So as a result, the the attacker they want to design such a Trojan that often get activated and have very rare conditions. So so how can we now? The question is how can we generate these variants, right? Because we don't have any existing tool to generate the most diverse variants. So as a result, we create a tool. So in the first part of our framework, we took our program and preprocessed it. By preprocessing, we means the user instead of the whole program, he or she might take only some part of the program, for example, a function, and instead of the all variables, they want to just take some of the variables, that is very important to them. So by after reprocessing the source code, we apply business optimization passes to generate a number of variants. And when we got those all the variants target specific, we use a secret metric we are calling metricated variant selection. So this metricated variant is nothing but we are analyzing all the output and operand frequency of the program, and from that we choose the most diverse variants. So after getting the most diverse variant, we integrate the variants in our source code and make single executable file. And yeah, that's the tree workflow of our tool. For example, here you can see, for example, for a single program, we generate three variants, and you can observe how different they are in terms of instruction and the registration in the same program. So they are all functionally equivalent, but the internal structure and the registries are very different. But now the question is how this the variant will solve the Trojan problem, right? So as a result, we did another analysis. The analysis where the probability of retriggering of same Trojan in multiple variables. So what we did, we took a program and we generate all the possible the design of Trojan, and what we observed, the number of Trojans in variant one, we generate the repeated probability of the same Trojan in variant three is drastically lower. So that means, our multivariate execution, there is high chance that if there is any anomaly in our site, we can able to detect it by running these multiple variants. So how are these variants generated? As we already told you, we are using all variants similarity, and from the user perspective, so first we need a configuration file, like the data type and the variable we want to protect, and then we process our source code, and after that we'll compile our source code using numerous operation sequences that is stored in a text file. And after running the operation sequences, we will get the intermediate representation of number of variables, and from that we will choose the most diverse variables. So the question is how multivariate execution will tolerate the Trojan operation. So as we already assumed that the Trojan will deal with it will change the output of a program. So if the outputs were changed of a variable or in a program, the execution of program set will tell me the comparison result will raise it back, and we run the other variables. So to prove our concept, we designed some Trojans and inserted this Trojan in a OpenBase CPU. And you can see that we use different trigger signals to design the Trojans. And we can design like conventional or sequential Trojan. And if you can observe, like variable one, when the Trojan is get activated, the output got changed, but for variable two and three, the output changed. But it is also happening. For example, the Trojan 6, the both variants got changed by the activation of the Trojan, but the third variant, the output is still the same. So in that case, we can say that we can detect the Trojan, but we can tolerate it. So it's kind of detection and the false both mechanism in our solution. So also we analyze the overhead and the execution time. So it is obvious that for smaller programs, the overhead percentage is very high. But when the design, the programs are increased, the overhead gets lower. For the execution time, the percentage of execution is almost about 150%, and it's kind of a trade-off between the performance over the security. So for future improvement, we are still thinking of like how we can address the different class of Trojans, because different function for Trojan, we know that there can be Trojan that can bypass some data from our microprocessor, right? Also, if the attacker they think about designing the Trojan using some fixed data, so how can we diversify the data to change the Trojan? To tolerate the Trojan activity. Also, we are thinking about tackling with time-sensitive applications for high performance programs. How we can tackle this Trojan insertion problem. Also, we are trying to estimate the optimal number of variants we can run. For example, 3 variants or 5 variants program. But which is the optimal number of variants we can run to tolerate Trojan? That's one important question. And last but not least, we are trying to here to explore the compiler phasing problems. We know that we can apply numerous optimization passes, and there is no need to apply this optimization pass. And it's really complex to get the most diverse variants for which optimization passes to analyze. So we are trying to explore the compiler phasing problems. For example, we are trying to solve it using some problems to generate the most diverse variants. Yeah. So thank you. If you have any question, please don't forget to ask.